All right, so the next topic we're going to talk about is buoyancy. So you guys are all probably familiar with buoyancy because you've gone swimming or floated in a pool or the ocean or whatever. So buoyancy is kind of defined as the apparent loss of weight of an object when you're placed it in a fluid. And it really, like there's this thing called the buoyant force, which is the force that acts upward on an object that's placed in a fluid. It can be any fluid, so it doesn't have to be a liquid necessarily. It could be like a hot air balloon. And the air is pushing up on that hot air balloon. But we're going to concentrate on fluids because that's a more concrete example that you guys are familiar with. So we've already talked about how pressure changes at deeper parts of a pool or a liquid. So the further down you get, the deeper in the fluid, there's a greater pressure. So that means there's a bigger force on that side, and there's a weaker pressure towards the top. So if you look at this diagram over here, it does a pretty good job showing you like this force upward comes from the differences in these pressures. So as you go deeper in the pool, there's a bigger pressure, and that means that there's a bigger force pushing you up at that point. So, anyway, another kind of idea that comes out with buoyancy or the buoyant force is known as Archimedes' principle, and that's the idea that the buoyant force is equal to the weight of the water it displaces. So this, if you imagine this can here, it's pushing water out of the space that it would normally be in. So if there was no can here, it would just be a pool of water. And when the can is there, it's displacing that amount of water to a new space in the pool. So the object displaces the same volume of the fluid that is submerged in the fluid, and that means that the buoyant force, the force that's pushing upward there, is equal to the weight of the fluid the object displaced. So that's Archimedes' principle, which you may or may not have heard. So I'm going through this equation because it's a little bit confusing. So the buoyant force we just said is equal to the weight of the fluid. So to get the weight of the fluid, you would need the mass of fluid times gravity. And we did this trick earlier where the mass is essentially equal to the density times the volume. So it's the density of the fluid that the thing is submerged in times the volume of the object that is submerged. So for this object, it would be the whole can here, where if you're only partially submerged, then it would only be the part that's under the fluid. And then you have the acceleration due to gravity. So that's just this equation, and that's how you figure out the buoyant force. So if the buoyant force is greater than the weight of the object, so if you imagine you had the two force arrows, you had one gravity arrow going down, and then you had a buoyant force arrow going up. We analyzed forces. We just looked at, okay, whatever one is bigger is going to win the tug of war or the contest, the pushing contest. And if the buoyant force, this force going up, is greater than the weight going down, then the object's going to float. So that kind of makes sense. And then the opposite of that, if the buoyant force is less than the gravity, so if gravity is bigger than the buoyant force, the object would sink. So that's essentially why things sink and float, is just looking at the buoyant force. And we'll kind of go ahead and go through a problem now. So in this problem, it reads a wooden board has the following dimensions. It's 0.2 meters by 0.15 meters times 0.1 meters. So that's the dimensions of the whole board. And it's floating in the water with the following dimensions submerged. So part of the board, as you can see here, is out of the water, and part of the wood is submerged. So we're really concerned about the part that is under the water, because that is the stuff you need. Oh, that's a bad arrow. That is the stuff you need to figure out the buoyant force. So it floats in the water, density 1,000 kilograms per meter cubed, because that's the density of water. And we're going to find the buoyant force acting on the wooden board first. So we're going to figure out how much is the water or fluid actually pushing up on the board. And then finally, we're going to find the density of that wooden board, which is a kind of an extension of this problem. So I already have it worked out over here. It's the same kind of ideas. I just have the work. Oh, sorry. I have the work underneath. Here's the right arrow. Underneath the green arrow. So the first part, we need to find the volume submerged. So the volume submerged would be the 0.2 times 0.15 times 0.07. So that's just length times width times height again. So that gets you 0.0021 meters cubed. So that's the first thing. I just took these dimensions that are submerged and figured out what's my volume submerged. And then I'm going to plug into this density formula. So again, or I'm sorry, not the density formula, sorry, the buoyant force formula. Let me get rid of that green box now. So again, this is the density of the water or the fluid. This is the volume that's submerged. So that's why I use this number and not the whole board, because notice again, there's some section of the board that's floating up. And then 9.8, which is the acceleration due to gravity. So if I multiply those three numbers, I get 20.58 newtons. All right. So so we have obviously the gravity force is going down, and the buoyant force is going up. And if it's just floating at the top, that means that these two are equal. What would happen if I submerged this whole board? So if I took this whole, I don't think I can take it, but we'll take another rectangle. If I took this rectangle shape here, oh, that's a circle. Sorry. That should be a rectangle. All right, so if you imagine that's my rectangle, and I took it and I pushed it underneath the water. So in order to get it to sink underneath the water, I'd have to actually push it down. And if I let go, if I like took my hand off of this and stopped holding it down, what would happen to this board? It would naturally float upward because the buoyant force is bigger than that gravity force. But when it gets up to this height and just starts floating, it's automatically kind of just made it so that these are equal, because if it was still, the buoyant force was still bigger, what would happen? The net force would be up and it would start accelerating upward, or if the gravity was bigger, it would start accelerating downward. So at this point, when it's floating at the top, it's in equilibrium. But if I kind of submerge this board underneath the water, it would float upward. So that 20.58 is the force of the buoyant force. It's also equal to the gravity of the wood. So part A we found this part A, we found the buoyant force acting on the wooden board, and the next part is to find the density of that wooden board. So we're going to use this gravity is equal to that buoyant force idea. So because it's floating right now and it's just at rest, it's not accelerating one way or the other, net force is zero, it's balanced, all those ideas that we talked about last unit, or 2 units ago, sorry, that they're equal. And then we know that that gravity is 20.58 because we just got that here, and that's equal to mg. So if we divide by 9.8, we get the mass of this board is 2.1 kilograms. And again, we're not looking for mass, we're looking for density, but we have that trick where we kind of use mass equals density times volume, or density equals mass divided by volume. So we're just using that density equation again. So we know the mass, and actually we know the volume because it was given to us, or the dimensions were given to us. So they gave us the volume that was submerged, and that's what we used for this buoyant force. But for this density of the whole board, we need the volume of the whole board. So it's the entire mass of the board divided by the entire volume of the board. So we plug into that, and so I just use 2.1, which is my mass, and divide it by the total dimensions, which is what we had up here, the 0.2, 0.15, and 0.1. And you get 700 kilograms per meter cubed. So that's the answer for the density of the wood. If you compare it, so this is the density of the wood. If we compare that to the density of water, so the density of H2O, try to get rid of that again. The density of water we said was 1,000 kilograms per meter cubed. Maybe not. There we go. Okay, so it's 1,000 for. Anyway, this unit here, there it is. It's 1,000. So if something floats, then that means that the density is less. So if it sinks, the density is going to be more. So this is the density of the wood. That's what we just solved for here. So again, just to clarify this, when you're talking about buoyant force, it's the density of the fluid that it's in times the volume that's submerged times gravity. So it's a little bit different than some of the other ideas that we've looked at in terms of over here. When we found the density of an object, you need the density or the mass of that object divided by the volume of that object. So it's a little bit kind of different in that sense. So you got to worry about, okay, what am I floating in or sinking in? What is the volume that's in that fluid? And then we got to multiply that by the gravity constant, which is always going to be 9.8 on Earth. Okay, so hopefully that helped, and we will. Sorry, got update. And we'll go with that for now. And I'm working on the buoyancy activity so that everybody can work on that as like a lab and kind of hopefully reinforce these ideas. So I will talk to you guys later.